Welcome to quantum numbers. So in the last video we talked about, we gave a little introduction to the quantum mechanical model of the atom. We said that just like the Bohr's model of the atom, we have electrons that are moving in orbits, but we said they're no longer spherical orbits. They no longer have to be circular orbits that are at a fixed distance away from the nucleus. They still have certain energies associated with them, but we need some other way of describing these orbits now. And so we come up with quantum numbers. So again, quantum means it's quantized. There are specific energy values associated with these things. So there are 4 quantum numbers that describe the state of an electron in an atom. So in order to describe exactly where an electron is, the state the electron is in, we need just four numbers. So we have the principal quantum number, which we symbolize N. We have the angular momentum quantum number, which we symbolize L. We have the magnetic quantum number, which we symbolize M sub L. And we have the magnetic spin quantum number, which we symbolize M sub S. So the principal quantum number, again N, describes the size and energy of the shell. So this is basically like the energy level in Bohr's atomic model. So N has integer values, positive integer values, so 1, 2, 3, and so on, all the way up to infinity. So that goes like this. So we have the nucleus in the center. The first energy value, the first energy level, has an N of 1. That's just like Bohr's energy levels. The next one has an N of 2, and so on. So as N increases, the electron's average position is farther from the nucleus, and the electron is in a higher energy level, higher energy orbital. But again, in the quantum mechanical model, the electron doesn't have to be these set distances from the nucleus like it had to be in Bohr's model. They're allowed to be in there in other distances from the nucleus, but I'm still showing Bohr's model of the atom here to get the idea across that the principal quantum number gives us different energy levels. So not that the electron is physically some set distance away from the nucleus, but it has some energy associated with it. Because again, it's acting like a wave. Alright, so the next quantum number, the angular momentum quantum number, or L, describes the shape of the suborbital. So L has integer values of 0, 1, and 2, and so on, going up to n minus 1. So n, remember again, was our principal quantum number. So if we have an electron that's in the first energy level, then n minus 1 is 0, which means only 0 is allowed. We can't have an L of 1. We can't have an angular momentum quantum number of 1 if the n value, the principal quantum number, is 1. So if we have an electron that's in the 4th energy level, well then we can go up to 4 minus 1, which is 3, so we can have 0, 1, 2, or 3. And so basically each energy level that you move out, as you increase n by 1, you increase the possible values of L by 1. Now, remember that I said possible values of L. It doesn't mean that n minus 1 is the value of L, but we can have values of L from 0 up to n minus 1. Which means if we have energy level 1, n of 1, we have one possible value of L, 0. If we have n of 2, we have 2 possible values of L, 0 and 1. So with 4, we have 4 possible values of L. With n equals 4, we have 4 possible values of L. We have 0, 1, 2, or 3. Those are all equally allowed values. So, now we've also given L values specific letters associated with these suborbitals. We've given L equals 0, S, L equals 1 is called P, L equals 2 is D, L equals 3 is F. Now, the reason why these are given these letters seems a little strange, but it comes from the line spectrum, and so S means sharp, P is from principal, D is diffuse, F is fundamental. We've basically deprecated those meanings, but the letters are so commonly used that we still use them But now, if we go past L equals 3 to L equals 4, we would just continue going from F alphabetically. So we'd have S, P, D, F, then G, H, I, J, and so on. Don't ask me what happens if we get to P again, but that's so far past what we actually fill up with an electron that we don't really have to worry about it. So now, remember that I said that this quantum number describes the shape of our suborbital. Now, each of these numbers, the 0 means an s orbital, a 1 means a p orbital, and so on. I'm going to, from here on, call them, or generally call them by the letters, not by the L numbers. So an s orbital has a spherical shape. A p orbital has sort of this two-lobe structure where in the s orbital, the nucleus is in the center there. In the p orbital, the nucleus is in the center there. Note that there's a node here in the center where the electron is not allowed to be. In the d orbital, again, we have the nucleus in the center. Now we have a four-lobe structure. It's starting to look sort of like a flower. Right? This just sort of looks like half of that, or this one looks like two of these. One of them turned sideways. Now, so again, the s orbital here has no nodes associated with it. It's just a spherical orbital. The p orbital has one node associated with it. It's got one plane in space this way. So note that all three of these are three-dimensional. But the p orbital has one plane. We're sort of imagine like we've taken this orbital and now we've put one plane through it that the electron is not allowed to be in, and the electron, the result will look something like this. And if we put two planes in there, two nodes where the electron isn't allowed to be in X shape like that, now the electron is going to congregate in the other areas that it is able to be in, and will have a shape that looks something like that. And so as we continue and go on, if we go to F, then we have a third node in here. Now that third node is in the plane of my screen here, and that splits this four-lobed structure into 8, but now it's a three-dimensional structure. So the next quantum number, the magnetic quantum number m sub L, describes the orientation of our suborbital in space. So whether it's aligned along the x, y, or z axis. Now, there is no real x, y, or z axis within the atom. We're just sort of picking one arbitrarily and saying, oh, well, this is the x, and this is the y, this is the z, right? But they're mutually perpendicular, so there's a 90-degree angle between any two of them. So the m sub L, our magnetic quantum number, has integer values ranging from negative L through 0 to positive L. So that means that if we have an s orbital, s, remember, was L equals 0. Well, if L equals 0, then we can go from negative 0 to positive 0. So the only value we can have is 0. So we can only have one value. If we have a p orbital, p had L equals 1, so we could have negative 1, 0, or positive 1. A d orbital had L equals 2, so we could have negative 2, negative 1, 0, positive 1, positive 2, and so on. So the number of possible values for m sub L is always odd. Then it's 1, 3, 5, 7, and so on as we go S, P, D, F, and continue on through G. Now again, this tells us which direction, which orientation in space we have. So for the p orbitals, let's say, remember we have 3 p orbitals, we have values of negative 1, 0, and positive 1. So one of them is going to be aligned along the x-axis, one of them is aligned along the y-axis, sort of coming out of the board, and one of them is aligned along the z-axis, going up and down. The next quantum number is the magnetic spin quantum number, m sub s, and this describes the magnetic spin orientation of the electron within the suborbital. So remember that the Earth has a magnetic field. This magnetic field protects us from a lot of the radiation that comes from the sun, so from the particles coming from in solar storms, those particles streaming through space run into the Earth's magnetic field and get directed to the poles. So if you lived, say, at the North or South Pole, or the North or South Magnetic Pole, you would get substantially more radiation from these solar storms than you do anywhere else on Earth. But the reason why Earth has a magnetic field is that its core is spinning, right? And so as Earth's core is spinning, it sets up some electrical currents in it which cause a magnetic field. So we have a similar sort of thing that goes on here with the electron. So you can think of an electron as spinning some direction. Now we don't really mean it's physically spinning in space like the Earth is spinning or Earth's core is spinning. But we mean that the electron has a certain magnetic orientation to it. And it only has two possible values. It either has a value of -1/2 or +1/2. So this is called spin down or spin up. Spin down is the -1/2, spin up is the +1/2. So this is similar to magnets where we have a north pole and a south pole to the magnet. It can either be facing one direction or the other. So again, our electron we can think of it as it's spinning. We can think of it as that spin is pointing either up or down. Right? Now it's not necessarily up or down in space, but it's sort of one of these two values, either sort of a north or south pole to it. Right? And that's what we mean here. So when we combine our four quantum numbers together, we have, again, n, our principal quantum number, L, our angular momentum quantum number, and so now we can give this combination of n and L some designation, some easier way of describing what we mean, of talking about what this suborbital is. So with n equals 1, we're in that first energy level, closest to the nucleus. That means that our possible L values are only 0. We only have that one possibility. That suborbital we call the 1s, 1 because it's in the first energy level, s because an L equals 0 is an s orbital. Now, the m sub L value there's only one possibility, that has to be 0. That means that we only have one orbital, and each orbital can contain 2 electrons, so we can only get 2 electrons into the 1s orbital. Now, we don't have any other suborbitals in the first energy level, so the first energy level can only have one orbital, which means it can only have 2 electrons. If we want to put in more than 2 electrons, we have to go to the next energy level, n equals 2. Now, n equals 2 has 2 suborbitals to it. It's got the L equals 0, which is the 2s, and it's got the L equals 1, which is 2p. Now again, the s, the 2s, has only one possible value for m sub L, and so it only has one orbital. It only can hold 2 electrons. The 2p has 3 possible values, because now we can go from -1 to 0 to +1 for m sub L. That means we now have 3 orbitals. Well, each orbital can contain 2 electrons, so 3 times 2 is 6. So our 2p can hold 6 electrons. If we want to put in any more electrons, we don't have any other orbitals. We've filled up the first energy level, we've filled up the second energy level, now we have to go to the third energy level. So with the third energy level, again, we have an S, we have a P, and now we have a D. Again, the D was L equals 2. So now we can have possible m sub L values of -2, -1, 0, +1, and +2. Again, the S has just one possible value, the P has 3. So we have one s orbital giving us 2 electrons, 3 p orbitals giving us 6 electrons, 5 d orbitals giving us 10 electrons. In the fourth energy level, we can continue this, so we have a 4s holding 2 electrons, we have a 4p holding up to 6 electrons, we have a 4d holding up to 10 electrons, then we get to the 4f with L equals 3. Now we have m sub L values of -3, -2, -1, 0, +1, +2, +3. So we have 7 possible values there, which means we have 7 orbitals, and that gives us 14 electrons, or up to 14 electrons that we can get in the fourth energy level. If we want to put in any more electrons, then we have to go to the fifth energy level. So, in this way you can see that, now note that I've only used 3 out of the 4 possible quantum numbers, because we still have the m sub s, which has 2 possible values. So, you note that each orbital has a combination of an n value, an L value. Those two tell us which designation it is, 1s, 2s, 2p, and so on. The m sub L, again, tells us which orientation in space it is. Now for an L equals 0 for an s orbital, it's spherical, so it doesn't really have a direction associated with it. The p values do, the d's do, and the s do. But for any one orbital, we can get 2 electrons in there because we can get 1 electron that's spin up, 1 electron that's spin down. So that m sub s value of -1/2 or +1/2. And so that combination of 4 quantum numbers, the n, l, m sub l, and m sub s. Now I haven't listed m sub s in here because they're all plus or minus 1/2. They're all going to be the same. So that combination of 4 quantum numbers describes an electron, describes the state of an electron, and it turns out that only 1 electron can have some combination of 4 quantum numbers. So again, to recap a little bit here, the n is our principal quantum number. We can refer to that as, that tells us which shell or energy level our electron is in. The physical meaning there is sort of the distance from the nucleus. It's really the energy that that electron has. But you can think of it as distance from the nucleus because they're somewhat related. The requirements there are that n has to be a positive integer. So it has to be 1 or greater, up to infinity. L is our angular momentum. That tells us the subshell, so the s, p, d, or f. That tells us the shape of the orbital, but not which direction it's facing. That has to be an integer value between 0 and n. That has to be between 0 and n minus 1. The m sub L is the magnetic quantum number. We call that the orbital. That tells us the orientation. Right? So the orbital here, we have multiple orbitals within a subshell. We have multiple subshells, or possibly multiple subshells within an energy level. And the m sub L value there has possible values of -1 to +1. It also has to be an integer. And then we have m sub s, our magnetic spin. So that's the spin on our electron. That's the magnetic spin on the electron as sort of the direction, whether it's sort of a north pole or south pole electron. And those have to be a half integer value, so either -1/2 or +1/2. So a note here on terminology is that an orbital is some region in space that can contain up to 2 electrons, and orbitals can overlap each other, so they're not mutually exclusive. A subshell is composed of 1, 3, 5, 7, 9, and so on orbitals, depending on the type, whether it's S, P, D, F, G, and so on, alphabetically from there. A shell or energy level is composed of multiple or possibly multiple subshells, so S, P, D, F subshells, but there's only one of any one of these in there. So there's in the 4th energy level, in the 4th shell, there's a 4s, a 4p, a 4d, and a 4f. The s only has 1 orbital in it, the p has 3 orbitals, the d subshell has 5 orbitals, the 4f subshell has 7 orbitals in it, and so on. And so be careful about which word you're using. Orbital, again, refers to some region in space that can hold only 2 electrons. So don't go calling, say, the 4th shell the 4th orbital, because that doesn't work. I'm trying to keep this terminology consistent. So that was quantum numbers.